a Canadian astronomer named Andrew McKellar measured the temperature of empty space. He wasn't trying to. He was studying faint absorption lines from cyanogen molecules drifting between the stars, and he noticed something odd. The molecules were not perfectly cold. Something was gently warming them, holding them at about 2.5 degrees above absolute zero. McKellar published the number and moved on. He had no way of knowing that he had just taken the temperature of the Big Bang, and that the answer would sit in the scientific literature, unread and ununderstood, for the next 24 years. That number was the first recorded contact between humanity and the oldest light in the universe. Tonight, that light has a name: the cosmic microwave background. And the story of how we found it, lost it, found it again, and then spent more than $4 billion learning to read it, is one of the strangest detective stories in the history of science. Let's start with the prediction. In 1948, George Gamow and his students Ralph Alpher and Robert Herman were working out what the universe would have been like if it had begun hot and dense. Their equations, built on Alexander Friedmann's solutions to Einstein's general relativity, said something remarkable. If the early universe really was a furnace, then the light from that furnace should still be here, diluted, stretched, cooled by billions of years of cosmic expansion, but here, filling every cubic centimeter of space, arriving from every direction at once. They even estimated its temperature, a few degrees above absolute zero. Then they did something that seems almost tragic in hindsight. They concluded that this fossil light was far too faint to ever be detected, and they let the idea go. For 17 years, the afterglow of creation was considered unobservable, and during those years it was very nearly discovered twice. In 1957, a young Soviet radio astronomer named Tigran Shmaonov was calibrating a horn antenna and kept finding a stubborn background noise he could not remove. It came from everywhere in the sky, day and night, in every season, at a temperature of roughly 4 degrees. He reported it in his dissertation and in a Soviet instrumentation journal. Nobody connected it to cosmology. Then in 1964, two Soviet theorists, Andrei Doroshkovich and Igor Novikov, published a paper that did everything except make the discovery itself. They calculated that Gamow's relic radiation should be detectable in a specific frequency window, a quiet gap between the synchrotron glow of our galaxy on one side and the emission of cosmic dust on the other. And they pointed out that the best existing instrument for the job was a particular horn-shaped antenna in New Jersey, built by Bell Laboratories. That is the part of the story that deserves a pause. A year before the discovery, someone had already named the telescope that would make it. At that antenna, two radio astronomers, Arno Penzias and Robert Wilson, were fighting a mystery of their own. They wanted to do sensitive radio astronomy, but their receiver kept registering an excess hiss they could not explain. They checked the electronics, they checked the wiring, they pointed the horn at New York City, then away from it. The noise never changed. Famously, they even evicted a pair of pigeons nesting inside the horn and scrubbed away what Penzias delicately called a white dielectric material. The hiss remained, uniform across the entire sky, corresponding to a temperature of about 3 degrees above absolute zero. Meanwhile, less than an hour's drive away at Princeton, a group led by Robert Dicke and Jim Peebles had independently rediscovered Gamow's idea and was building an antenna to search for exactly this signal. When Penzias learned of their work through a chance phone conversation, the two groups met, compared notes, and realized what had happened. In 1965, the Astrophysical Journal published two papers side by side, one from Bell Labs describing the mysterious noise, and one from Princeton explaining what it was. Penzias and Wilson had discovered the relic radiation of the hot early universe by accident, while trying to get rid of it. In 1978, that accident earned them the Nobel Prize. Shmaonov's earlier detection and Doroshkovich and Novikov's roadmap faded into the footnotes of history. So what exactly did they find? Here we need to rewind the universe. For the first 380,000 years after the Big Bang, the cosmos was a glowing plasma, a dense fog of electrons, protons, and photons, so hot that atoms could not hold together. Light could not travel in a straight line. Every photon ricocheted from one free electron to the next, trapped like a flash of light inside a thundercloud. Then, the universe expanded enough and cooled enough for something decisive to happen. At around 3,000 degrees, electrons finally settled into orbit around protons, forming the first stable hydrogen atoms. The fog cleared, and the light that was in flight at that exact moment has been traveling in straight lines ever since, for 13.8 billion years, stretched by the expansion of space from orange-hot glow into cold microwaves. When your instruments pick up the cosmic microwave background, you are photographing the universe as it looked at the moment it first became transparent. It is, quite literally, the oldest photograph that can ever be taken. And here it's worth stopping to clear away the most stubborn misconception in all of cosmology. The Big Bang is commonly imagined as an explosion, a bright point in empty space, hurling matter outward like shrapnel, with the universe expanding into some pre-existing void. That picture is wrong in nearly every detail. The Big Bang did not happen at a point. It happened everywhere at once because it was not an explosion in space. It was the rapid expansion of space itself, with everything inside it hot and dense at the same time. There is no center to point a telescope at, and no edge racing away from us. The proof surrounds us on all sides. The microwave background arrives from every direction with almost exactly the same temperature, which is precisely what you'd expect if the whole universe was once uniformly hot, and precisely what an explosion from a single point could never produce. There is a second, subtler surprise hiding in the textbook definition. We say the microwave background was born 380,000 years after the Big Bang. But that is only the moment the photons were released. The photons themselves are far older, and their origin is stranger than most people ever hear. In the first instance of the universe, matter and antimatter existed in almost perfectly equal amounts. Almost. For every billion antiparticles, there were 1,000,000,001 particles of ordinary matter. When the universe cooled, matter and antimatter annihilated in a cataclysm that converted essentially everything into light and left behind only that 1 in a billion excess of matter. That leftover is us. Every star, every planet, every atom in your body is the rounding error of that annihilation. And the flash it produced is the very sea of photons that would later scatter through the primordial plasma for hundreds of thousands of years before escaping as the microwave background. Count the photons in the universe today, and you find roughly 1,000,000,000 of them for every proton, the exact arithmetic of that ancient act of mutual destruction, still written across the sky. Those hundreds of thousands of years spent bouncing through the plasma did something else remarkable. They gave the radiation a perfect thermal spectrum, and perfect is not a figure of speech. Physicists have a gold standard for thermal radiation called a blackbody spectrum, the precise mathematical curve produced by matter and light in complete equilibrium. Nothing we have ever observed on Earth or in space matches it exactly. Stars come close but carry absorption lines. Planets, dust clouds, galaxies all show distortions. In the entire known universe, exactly one thing radiates as a mathematically flawless blackbody: the cosmic microwave background. When NASA's COBE satellite measured its spectrum in the early 1990s, the data points fit the theoretical curve so precisely that the error bars were smaller than the width of the drawn line. When that plot was first shown at a conference, the audience of astronomers did something audiences of astronomers essentially never do. They stood up and applauded. John Mather, who led that measurement, shared the Nobel Prize for it, because a perfect blackbody at 2.725 degrees is something no swarm of stars, no warm dust, no instrumental artifact can fake. Only a universe that was once entirely a furnace can produce it. COBE's second discovery was even more consequential. The background is not perfectly uniform. It carries tiny temperature ripples, fluctuations of about 1 part in 100,000. To appreciate what it took to see them, consider what the measurement is up against. The signal is drowned beneath the microwave glow of our own galaxy, the emission of the atmosphere, the noise of the instruments themselves, contamination up to 10 million times stronger than the pattern being extracted. Many careful scientists doubted the ripples could ever be pulled out of that noise. They were wrong. George Smoot's team mapped them in 1992, and those faint blotches, the famous first baby picture of the universe, turned out to be the seeds of everything. The slightly denser regions that gravity would spend billions of years amplifying into galaxies, clusters of galaxies, and eventually into observers capable of looking back at the map. Before we read the ripples, the map holds one more secret. This one about us. Lay the raw temperature measurements across the sky, and the strongest pattern you see is not cosmological at all. One half of the sky is very slightly warmer. The opposite half very slightly cooler, by about a part in 1,000. This is a Doppler effect, the signature of our own motion. The sun, the earth, the whole Milky Way are plowing through the sea of ancient photons at roughly 600 kilometers per second toward a point in the constellations near Leo, compressing the light ahead of us and stretching the light behind. Which means the microwave background quietly hands us something physics students are taught doesn't exist: a universal reference frame, a way to define, unambiguously, how fast anything is moving relative to the universe as a whole. This is not the luminiferous aether of the 19th century, and it breaks none of Einstein's rules. Relativity forbids a frame in which the laws of physics change, not a frame defined by what the universe happens to contain. But it is still a quietly astonishing fact. There is a rest frame of the cosmos, and we know our speed through it to better than a fraction of a percent. Subtract our motion, mask out the galaxy, and what remains is the treasure, that speckled pattern of hot and cold spots, each a snapshot of a sound wave frozen mid-oscillation, because that is what those spots are: sound. In the primordial plasma, gravity kept pulling matter into the denser regions while light pressure kept pushing it back out. The result was acoustic oscillation, the entire universe ringing like a struck bell, with overtones, for 380,000 years. When the fog cleared, the pattern of compressions and rarefactions was flash frozen onto the sky. The size of the spots tells you which notes the universe was playing and how loudly. Cosmologists compress all of it into a single graph, the angular power spectrum, which simply asks how much temperature variation exists at each spot size. Take a window 90 degrees wide and measure the variation across the whole sky. Shrink the window and measure again and again, down to a fraction of a degree. Plot the results, and a curve rises from the data with a series of majestic peaks, like the profile of a mountain range. First peak, second, third, and onward. One respected radio astronomer liked to tell students, only half joking, that in 6,000 years of civilization, pyramids, calculus, antibiotics, the internet, the most profound single artifact humanity has produced is this curve, because folded into its shape is the answer to nearly every question you can ask about the universe as a whole: what it is made of, how it has expanded, what its geometry is, and what happened in its first fraction of a second. Here is the number that should stop you cold. To reproduce that entire curve, every peak, every valley, measured across 2,500 independent points on the sky, distilled from billions of measured pixels, the standard model of cosmology needs exactly 6 numbers. 6. The density of ordinary matter, the density of dark matter, the strength of dark energy. 2 numbers describing the primordial seed fluctuations, their amplitude, and their tilt. And 1 number marking the era when the first stars switched on. Feed 6 parameters into the equations, and out comes the observed sky in exquisite detail. 6 numbers to specify a universe. The model is called lambda CDM, lambda for dark energy, CDM for cold dark matter, and no rival cosmology, none can reproduce the shape of those acoustic peaks. The way those peaks were confirmed reads like a controlled experiment performed on the entire cosmos. In the early 2000s, NASA's WMAP satellite measured the first 3 peaks with precision. From those 3 peaks alone, cosmologists fixed the 6 parameters and then did what real science demands. They predicted, in advance, exactly where every subsequent peak would fall. Then the European Space Agency's Planck satellite flew with better detectors and finer resolution and measured peaks 4, 5, 6, 7, and beyond. Every one of them landed where the model said it would. That is the difference between fitting data and understanding a system. The universe was asked to show its hand, and it matched the prediction to within fractions of a percent. This is what researchers mean by the era of precision cosmology. Within living memory, cosmology was a field where respected scientists disagreed about basic quantities by a factor of 2 and did so for decades. Today, the age of the universe is quoted as 13.8 billion years with an uncertainty of a few tens of millions, a measurement good to a fraction of a percent. The total bill for this transformation, every experiment ever aimed at the microwave background, from balloon-borne detectors over Antarctica to the great satellites, comes to more than $4 billion. It may be the best money the species has spent, because the information encoded in that light is not available anywhere else at any price. And the map keeps giving, because the ancient light did not travel to us through an empty universe. It traveled through 13 billion years of evolving cosmic structure, and the journey left fingerprints. When a photon falls into the gravitational well of a growing supercluster, it gains energy. Climbing out, it pays the energy back. But if dark energy has stretched and shallowed the well during the crossing, the photon exits with a tiny profit. Measure those subtle warm patches, and the microwave background becomes an independent witness to the accelerating expansion of the universe. Elsewhere, photons passing through clusters of galaxies get kicked to higher frequencies by collisions with hot electrons, an effect predicted by Rashid Sunyaev and Yakov Zeldovich in Moscow years before anyone could measure it, and now a standard tool for discovering distant clusters. And the intervening dark matter, invisible in every telescope ever built, betrays itself by gravitationally bending the paths of the ancient photons, a smearing so subtle and so statistically precise that the Planck team inverted it to draw a map of all the dark matter in the observable universe, silhouetted against the light of creation. Each of these effects is also a test that could have failed. If the microwave background were some local fog, starlight reprocessed by dust, as skeptics once argued, none of this would hold together. A reprocessed glow would not carry acoustic peaks. It would not lens, and it would fail the most elegant check of all. Distant gas clouds, seen as they were billions of years ago, should have been bathed in a warmer background. The universe was more compressed then, so the relic radiation must have been hotter in exact proportion to the redshift. Astronomers have measured the temperature of the background in the deep past using interstellar molecules as thermometers, the same trick McKellar stumbled on in 1941, and it rises with distance precisely on schedule. The fossil light behaves, in every testable way, like the cooling ember of a once-hot universe. But the deepest question the map can answer is about the very beginning. Where did the ripples come from in the first place? What planted the seeds? The leading answer is inflation. The proposal that in its first unimaginable sliver of a second, around 10 to the minus 35 seconds, the universe underwent a burst of exponential expansion, stretching faster than light stretches through space. And inflation makes a claim that ought to sound like mysticism, but is actually testable physics. The seeds of all cosmic structure were quantum fluctuations of the vacuum. Empty space is not empty. Pairs of virtual particles constantly flicker into existence and annihilate. Ordinarily, they vanish without a trace. But if space itself is doubling in size faster than the pair can recombine, the two partners are torn apart and stranded. The fluctuation is caught, frozen, and stretched to astronomical scale. It is the same physics, incidentally, by which black holes are predicted to evaporate. A virtual pair split by a horizon, one partner lost, one made real. Run that process through inflation, and the arithmetic leads somewhere staggering. Every cluster of galaxies on the sky descends from a quantum tremor once smaller than a proton. The Virgo cluster, with its trillions of stars, is a vacuum fluctuation that got promoted. Extraordinary claims need signatures, and inflation has left several. It predicts the universe should be geometrically flat, because stretching any curved surface enormously makes it locally indistinguishable from flat, and Planck measures the curvature of the observable universe as 0 to within a few thousandths. It predicts the fluctuations should be Gaussian, pure, structureless randomness, the statistics of the vacuum itself, and they are to the limits of measurement, and it makes one exquisitely specific numerical prediction. If the seeds were quantum fluctuations stretched by inflation, then their strength should not be perfectly equal across all scales. Large ripples should be very slightly stronger than small ones by a few percent. Vyacheslav Mukhanov and Gennady Chibisov calculated the expected tilt back in 1981, a number close to 0.96, where exact scale equality would be 1. 3 decades later, Planck delivered the verdict, 0.965, with an error bar in the third decimal place. A prediction from quantum theory about the first trillionth of a trillionth of a trillionth of a second, confirmed by a satellite map of microwaves. One smoking gun is still missing. Inflation should also have generated primordial gravitational waves, ripples in spacetime itself, stretched to cosmic proportions. And those waves would twist the polarization of the microwave background into a faint swirling pattern called B-modes. In 2014, the BICEP 2 telescope at the South Pole announced it had found them. Champagne was opened. Nobel Prizes were confidently forecast. Within months, the signal collapsed. The team had underestimated the polarized glow of dust in our own Milky Way. They had discovered, at great expense, our galaxy. It stands as a cautionary tale about wanting a result too much, and the successor experiments now running in Antarctica are pushing the sensitivity lower year by year. If the swirl is found, it is a direct image of quantum gravity at work at the birth of the universe. If it is convincingly ruled out, whole families of inflationary models die, and theorists get what one lecturer wryly called a new holiday, the freedom to invent something better. The map has been interrogated for stranger possibilities still. If the universe had an exotic shape, if space closed back on itself like a three-dimensional torus or a dodecahedral hall of mirrors, as one serious proposal suggested, then light circling the cosmos would stamp repeating, matched patterns onto opposite sides of the sky. Cosmologists searched for them. Nothing. If cosmic strings, one-dimensional defects in space-time, relics of the universe's earliest phase transitions, threaded the cosmos, each would slash a characteristic knife-edge discontinuity across the temperature map. Searched for, down to 1 part in 10 million, nothing. If the universe rotated or expanded at different rates in different directions, the fluctuation statistics would skew in measurable ways. They don't. Even the constancy of the laws of physics gets tested, and the fine structure constant measured across the sky and across cosmic time refuses to budge. Each null result sounds like an anticlimax. Each is actually a triumph, an entire universe of possible exotic cosmologies, closed by one map. Honesty requires saying that the map also contains things nobody fully understands. The two largest ripple patterns on the sky, the quadrupole and octopole, line up with each other along a direction that journalists gleefully christened the axis of evil. When pure chance says they should be independently oriented, there is a cold spot in the southern sky larger and colder than Gaussian statistics comfortably allow. The odd-numbered harmonics carry systematically more energy than the even ones, as if the universe had a parity preference. Are these profound clues or coincidences amplified by the human talent for finding patterns, contaminated perhaps by the foreground of our own galaxy, whose plane and motion lie suspiciously close to some of these alignments? The sober answer is that we cannot yet rule out either option, and there is a deeper limitation underneath. We have exactly one sky. Cosmology is the only science whose experiment cannot be rerun. Every statistical fluke we might dismiss in a laboratory must here be argued about forever, because the sample size of universes available for observation is one, and one anomaly has grown from curiosity into full crisis. Measure the current expansion rate of the universe, the Hubble constant, from the microwave background, and lambda CDM answers 67 kilometers per second per megaparsec with superb precision. Measure the same number directly from the recession of nearby galaxies calibrated with exploding stars, the method of Nobel laureate Adam Riess and colleagues, and the universe answers 74. The two camps have checked, rechecked, and sharpened their measurements for a decade, and the disagreement has hardened past 4 sigma, well beyond comfortable dismissal. Perhaps some subtle systematic error lurks in the ladder of supernova calibrations, as many microwave cosmologists privately suspect. The background measurement rests on billions of data points and a transparent, reproducible pipeline, while the supernova route leans on a chain of calibrations, each a potential weak link. Perhaps we happen to live inside a local underdensity that skews nearby measurements. Or perhaps the thrilling option, the 6-parameter model is missing a piece of physics, some new ingredient acting in the dark between the first light and today. It is worth remembering for humility that measured values of the Hubble constant have wandered from 600 down to 67 over the past century, with each era's astronomers armed with certainty. The tension is either an accounting error or the first crack in the finest theory of the universe ever constructed. As of now, nobody on Earth knows which. How can 6 numbers be pinned down so tightly? Because the sky is savagely overdetermined. Ask how many independent quantities you could in principle read off 8 acoustic peaks. Each has a position, a height, a width, and simple counting already gives you 24 measurements chasing 6 unknowns. But the real bookkeeping is far more lopsided. The power spectrum is not 8 peaks. It is 2,500 independent data points, each one a separate measurement of the universe, and behind them stand the billion individual pixels of the map itself, 6 free parameters, 2,500 equations. The system is so over-constrained that cosmologists can slice the spectrum into pieces, fit each piece separately, and check that every fragment of the sky votes for the same universe. In the final Planck analysis, released in 2018, every fragment does. And the fitting machinery is public. The computer codes that turn maps into cosmological parameters are open source, downloadable by any student with a laptop. Anyone who suspects the cosmologists of fooling themselves is welcome to rerun the universe. There is a second, almost independent witness folded into the same light: polarization. When the primordial photons made their final scatter off free electrons, the geometry of that last collision left each photon with a faint directional preference, a pattern imprinted across the sky at the level of parts per million. This so-called E-mode polarization is a separate dataset, with its own peaks, carrying its own record of the acoustic oscillations. If the temperature map and the polarization map disagreed about the universe, the whole edifice would crumble. They agree. And polarization carries one bonus: the temperature map states only weakly. When the first stars ignited, their ultraviolet light re-ionized the cosmic hydrogen, and the freed electrons scattered a fraction of the relic photons one last time. That fingerprint dates the end of the cosmic dark ages, first starlight a few 100 million years after the Big Bang, the ionization of helium requiring the harder radiation of the first galactic nuclei somewhat later, a satellite tuned to microwaves, dating the dawn of stars it cannot see. One habit of mind separates this field from comfortable sciences, and it is worth naming. The researchers who built these maps will tell you plainly that they cannot prove the map is clean. The foreground of our own galaxy must be modeled and subtracted. The processing pipeline leaves faint statistical scars, and the one realization of the sky we possess can never be compared against a second draw. What they can do is torture the data, split it by frequency, by hemisphere, by season, by instrument, and confirm that the cosmology refuses to change. That is not certainty. It is something better earned, a result that has survived every attempt by its own authors to kill it. Step back and consider what this fossil light has quietly settled. It fixed the universe's age to a fraction of a percent. It weighed the cosmos and returned an inventory that should embarrass us. 5% ordinary matter, 27% dark matter, 68% dark energy, a universe in which everything ever seen through every telescope is a 5% impurity. It counted the neutrino families, 3 from temperature patterns alone, in perfect agreement with particle accelerators on Earth, and set limits on the neutrino's mass, sharper than any laboratory experiment. It verified that the universe cooked up precisely the predicted amount of primordial helium in its first half hour, a single map answering questions from particle physics to geometry, and the archive is nowhere near exhausted. 1 billion measured points on the sky against a few dozen equations means generations of unmade discoveries are still sitting in the data, waiting for someone to think of the right question. Researchers entering the field today are told, without irony, that the map already contains enough unread information for a century of careers, a library checked out once, barely opened. There is a final way to think about the microwave background, and it may be the most striking of all. That map is not ours. Any civilization, anywhere in the observable universe at any epoch, has access to the same sky, not the same pattern of spots, since each location receives light from its own horizon, but the same statistics, the same acoustic peaks, the same 6 parameters, the same physics. It is the one text every technological species must eventually discover and learn to read. A shared inheritance written at the recombination epoch, legible to anyone who builds a sufficiently good antenna, whatever their biology, whatever their mathematics, whoever they are. If the universe has a common language, it is written in microwaves. The light is still arriving. It falls on your rooftop at this moment, 370 trillion photons striking every square meter every second, the annihilation flash of the first instance, the frozen music of the plasma, still faintly warm after 13.8 billion years, still carrying answers we have not yet learned to ask for. Andrew McKellar measured its temperature in 1941 and never knew what he held. Penzias and Wilson tried to scrub it away with pigeon traps. We now know it is the deepest archive in existence. Somewhere in its unread pages may lie the resolution of the Hubble tension, the fingerprint of primordial gravitational waves, the true story of the first second. The oldest light in the universe has been answering our questions for 60 years. The measure of the next 60 is what we think to ask it.